Okay, so video one should have given you a good grasp on exactly what fundamental units are and the purpose of having consistent natural references for these units. So, as of today, what are the master references for all of the units shown here? Let's start with time. The official second today is based on the period of the electromagnetic radiation emitted by a cesium 133 atom, something crazy like that. Scientists are working to obtain an even better reference for the second, also using cesium 133 and I think lasers, to where the duration of whatever the atom is doing would be so consistent over time that after something like 14 billion years, if you made a graph of the duration lengths plotted against time, then those lengths would only be off by like 100 magnitudes after 14 billion years. So this is much more precise and consistent than what the electrical pulses in a supercomputer microchip could reproduce, like we talked about in the last video. Notice though, you have to keep an atomic clock running and sensing these cesium properties at all times, all day, every day. If something or someone needs to reference this very precise second, then they'll need a continuous live feed. If the clock isn't running, then no computer or person knows what the second is, because remember, a computer can't just save it. It's way too precise. So if an atomic clock is running all day, every day, I guess all computers and satellites can use the internet to communicate with it. Or maybe once scientists figure out how to get a big, bulky atomic clock like the one shown here working, then they'll work to make smaller, more compact ones. I'm not sure exactly, but a continuous 24/7 sensing of that cesium property is a must. If something, you can't save it, you're going to need it on you at all times if you're a computer or a scientist. Okay, so there's today's official second. What about length? First of all, like we talked about in the previous video, all lengths like the kilometer, the foot, inch, mile, etc., these lengths work their way back to the meter at some point. So, okay, then, well, what is the meter? The official definition for the meter is based off of the speed of light. The meter is officially defined as the distance light travels in 1 over 299,792,540, fractions of a second. So the meter references back to nature using the rate that light is moving through space. You break down each incremental step that light moves based on the cesium 133 atom second property. And so the distance that light moves in one of those increments is the meter. The rate that light is moving through space. Let's talk about this. We all know the official number corresponding to the speed of light in a vacuum is 299,792,548 meters per second. So the first question you might ask is, how can we possibly know that speed to every one of those significant figures? Well, that gets back to the fact that, remember, there have been countless scientists over the centuries who have devoted their lives to studying nature. The experiments these guys do are extremely sophisticated, and something like the calculation of the speed of light has been peer reviewed, critiqued, and criticized over and over and over again throughout the centuries. These scientists make genius correlations that they verify by experiment. So, like you can see below, even though there is a large gap in technology difference between those two pictures, the findings of Einstein and researchers of today build upon what researchers discovered in the past. The second question you might ask is, so wait, this value for the speed of light, that was discovered years ago. In the 80s, we redefined the second based on the cesium 133 atom, and that speed of light value was discovered by Einstein or something. Don't we have to redefine the speed of light now using the newly defined second? Okay, well, Today's second and meter are the same as the ones Newton and Einstein used in terms of magnitude. The difference today, though, is in terms of precision. The cesium-133 atom duration property was chosen and defined to match previous definitions of seconds in history, like, for example, the 1 meter, 1 kilogram pendulum swing. The two durations between then and now aren't going to be different in terms of magnitude, but the number of significant figures attached to the two durations will probably be different. So, like, okay, so today maybe we can define the speed of light based on fractions of a meter, and back 100 years ago they couldn't do that. So, okay, there we go. To get the worldwide accepted standard for the second and meter, all you need to do is go to a lab that has sufficient equipment. That's nice. You can do it anywhere you want. You don't have to reference something in France, some physical reference in France. And how exactly scientists keep this live second feed going for experiments, I'm really not sure. But just to note, people who make meter sticks to send them off to department stores or Lowe's, I wouldn't think use the speed of light to produce these master meters. A physical reference housed in a vacuum chamber, I would think, is plenty precise enough for activities like construction, roads, bridges, etc. Okay, what about the official mass reference? As of today, the official mass is still an actual physical piece of mass housed in France or something. So every so often they take out the official kilogram shown here out of this chamber, make a bunch of copies and send them to governments around the world, who make more copies and send those copies to mechanical and digital scale makers. Even in the vacuum chamber, though, the kilogram's mass can't be kept consistent enough for the precision certain scientists around the world need. So they're looking at a perfect sphere of silicon. This would be even more precise, because I think instead of weighing the silicon sphere, they make copies by matching up X-ray properties that count the planes of atoms in the sphere or something like that. But still, though, a silicon sphere is not a naturally occurring repeating phenomena like we have for the second and meter. Scientists today are still looking to find a consistent mass reference that reproduces itself in nature. But again, though, just like a meter stick housed somewhere, a physical mass reference in a vacuum chamber, I would think, is plenty precise enough for most normal tasks and jobs in life, like your bathroom scale, designing buildings, roller coasters, bridges, etc. Amount of substance. So the mole. Remember from chemistry, the mole is just 6.022 times 10 to the 23rd of anything. It's just a definition. Like a dozen equals 12 of anything, well, a mole is just 6.022 times 10 to the 23rd of whatever you're talking about. I could have a mole of donuts. That means I have 6.022 times 10 to the 23rd donuts. A mole of coffee beans, a mole of cars. But what the mole was really created to refer to was atoms. When using the word mole, you'll be saying you have a mole of atoms. We use this big number to simplify the conversation when discussing the actual number of atoms of a substance you are dealing with. This comes into play with chemists, pharmaceuticals, biology, where you want to have an idea of how many atoms you're dealing with in a chemical reaction, right? Because in a chemical reaction, one atom or molecule is reacting with one other atom or molecule. Okay, well, what is this random number 6.022 times 10 to the 23rd? Where did that come from, and how do we use it as a reference for the number of atoms we have in front of us? 6.022 times 10 to the 23rd, or Avogadro's number, is the number of atoms in 12 grams of carbon-12. That's its definition. Carbon-12 being the most abundant isotope of carbon on Earth. So it was like carbon black. Carbon-12, that's carbon black. So how could we possibly know that number? There's no way, right? It's impossible. Two things. First of all, I am going to reference what I talked about earlier the sophisticated experiments and life's work of scientists over the centuries, extreme critiquing, peer reviewing, etc. The second thing I'll say is this number isn't as accurate as it looks. You could be off by 5 quadrillion atoms and you're still within the constraints of the number. Okay, so like I just said, we know that the number of atoms in 12 grams of carbon 12 is within the constraints of this number. Still, how do we use that as a reference to find the number of atoms in another substance? Here's how. First, remember that the mass of one proton and one neutron are pretty much equal. They vary by a tiny percentage, and the mass of the proton and neutron are significantly greater than the mass of the electron. So the electron mass is a tiny percentage of the proton and neutron mass. Because all atoms in matter are made purely of protons, neutrons, and electrons, then to find the mass of any atom or substance, all you do is just add up the number of protons and neutrons in that atom and neglect the electrons. What this tells us is that because we know that we have 6.022 times 10 to the 23rd atoms sitting in front of us when we weigh out 12 grams of carbon 12, then when we weigh out 1 gram of carbon 12, we know that what is actually sitting in front of us is 6.022 times 10 to the 23rd protons and neutrons. It doesn't seem like this is the case because, look, it's black. That's black carbon sitting right there. But no, remember, that's literally just a pile of protons, neutrons, and electrons. That's what all substances are. So what this tells you now is if you were to weigh out 16 grams of oxygen, then that would mean you have 6.022 times 10 to the 23rd atoms or 1 mole of oxygen sitting in front of you. This is because we know oxygen has 8 protons and 8 neutrons in its nucleus. And we also know that each of those grams represents 6.022 times 10 to the 23rd protons and neutrons. So there's the mole. There's the amount of substance, fundamental unit. You might be wondering now, well, wait a minute. Isn't mass and amount of something kind of the same thing? Yeah, so if I'm a chemist, all I'm doing is converting back and forth between atoms and grams. The number of atoms in a bowling ball is just another way of describing the mass of the bowling ball, right? The difference is that, remember, we kind of talked about this in the basics of the universe video. We don't know what exactly mass is. In fact, as of today, we believe energy and mass are actually the same thing. E equals mc squared, right? The masses of things increase as their energy increases. If you rest a baseball on a very, very sensitive scale, it weighs one thing. But then if you spin the ball, the weight will increase slightly. And it doesn't increase because of the friction of the spinning ball. The mass of the actual baseball literally goes up. So when you think about something's mass, it's not so much about how many atoms you have in front of you. It's more of a property related to how hard something is being pushed back on by Earth based on how much mass it has, so like its weight, or how hard it is to accelerate something based on how much mass it has, so like its inertia. Temperature. Temperature is an objective measurement of hot or cold, and it is measured using a thermometer. Typical thermometers you see in everyday life are glass tubes filled with some sort of expanding and contracting liquid like mercury on the inside. The liquid will expand or contract depending on how hot or cold it gets when coming into equilibrium with the surrounding temperature. There's also those mechanical thermometers you're used to seeing. These use a bimetallic strip to output temperature. Two different metal strips are bound together. The different metals expand or contract different amounts depending on the temperature. So the strip moves a good bit at different temperatures. You just connect this movement to a needle and calibrate the needle to where it lines up properly on the temperature scale. If you need extremely precise measurements, you can use a digital thermometer. With a digital thermometer, there's no expanding and contracting liquid or metal strip. It will probably be something like the electrical current through a wire will change by tiny amounts based on tiny changes in temperature, and the built-in computer will pick up these changes and output a value for you. I'm sure you can buy extremely expensive thermometers that are incredibly precise. So, if you are building your own thermometer, whether it be liquid in glass, some sort of mechanical output, or digital, and you need to calibrate it. So, meaning how exactly are you going to mark and label the scales? If you are making a Celsius thermometer, you want to make sure that the liquid rests at the 0 degree mark. At the 0 degree mark, when in contact with water that is going through the process of freezing or melting, so like an ice bath. And you want to make sure that the liquid rests at the 100 degree mark when in contact with water that is in the process of boiling. Then just make sure equal you have equal interval tick marks above, below, and in between your two references. I drew a pretty coarse scale here. Each individual tick mark represents 10 whole degrees. In real life, though, you would have a longer tube, so you could space out at least 100 tick marks, probably even more than 100. Also, you want to make sure to put a round number of tick marks in between the 0 and 100, right? You wouldn't want to put 90 tick marks. If you did that, then that would mean each line doesn't represent 1 degree, 2 degrees, 3 degrees, etc. You would have decimal numbers. Your ticks would represent decimals. I would think all thermometers around the world are made at the same atmospheric pressure, probably the accepted pressure for average sea level. Remember, this is because it takes less thermal energy to boil water at higher atmospheres or higher altitudes, because the atmospheric pressure pushing down on the water is lower. If you take any thermometer to Denver or up Mount Everest, the temperature reading at boiling will be less than 100. And also, I'm thinking all thermometers are made using pure water. So, for example, you wouldn't want to use salt water or water with chemicals mixed in, because chemicals block water molecules from escaping and vaporizing. So, the boiling temperature would be higher in this situation. You could make a thermometer using salt water in Denver, but you would need to indicate this on your scale. And also, people would be annoyed because remember the centralized theme of these last two videos. If you had a thermometer made in Denver in reference to the freezing and boiling points of salt water, how would anyone know what any of those readings mean? They have nothing to compare that to in their heads. No one in the world ever uses that or ever has used that. Growing up, your idea of temperature readings aren't based on a thermometer scale made using that method. If you are making a Fahrenheit thermometer, then make sure the liquid rests at the 32 degree mark when in contact with water that is in the process of melting or freezing, and make sure that the liquid rests at the 212 degree mark when in contact with water that is in the process of boiling. Again, do this at sea level with pure water, and make sure to put a round number of tick marks in between. And like I said, digital or mechanical thermometers, it's the same thing. Just make sure the output and scale match the freezing and boiling points of pure water at standard pressure. The Kelvin scale is an absolute temperature scale. It is just the Celsius scale shifted back negative 273.15 temperature units. What this means is that to convert between Kelvin and Celsius, you are just adding or subtracting 273.15. 0 on the Kelvin scale is the coldest possible temperature in the universe. Remember from the What is Energy video, temperature is just a measure of the average mass motion or kinetic energy of the particles of a substance. So what absolute zero means is that if a substance has a temperature of absolute zero, then the particles of that substance have no motion whatsoever. Humans have never been able to create a temperature of absolute zero in real life. So again, this creates a question: how do we know the value of absolute zero? The answer to this is actually pretty straightforward. Just make a graph of volume versus temperature degrees Celsius. You can easily go below the freezing point of water, right? So make sure to put a negative temperature section as well. There's no such thing as zero volume, so volume will end at 0. Get a bunch of different balloons, each filled with its own unique gas. Start changing the temperature of each balloon and record the volume on the graph corresponding to each temperature. Now, there's going to be a limit to how cold of a temperature you will be able to perform your test, right? But what's interesting is when looking at your graph, every single line for each gas seems to converge at a point. And this is actually what would happen if you perform this test in real life using ideal gases. Ideal gases, remember from chemistry, I'm not going to go into what ideal gas is. I didn't draw the yellow line correctly, but it would be sloped similarly to the other gas lines. But anyway, so they all converge at a point, and amazingly, this point is on the x-axis, which corresponds to zero volume. There's no such thing as a negative volume, so zero volume just means that there's absolutely no atom movement whatsoever. So it stands to reason that there's no such thing as a temperature reading below this point as well. This point on the x-axis corresponds to a temperature of negative 273.15 degrees Celsius. So there you go. For a better perspective on the physical realities of our universe, let's create a new temperature scale by shifting the x-axis over to where 0 degrees is at this negative 273.15 point. Cut off the back end because there's no physical reality here, and rename this new scale the Kelvin scale. So if you're making a liquid or digital thermometer using the Kelvin scale, then mark the point water is in the process of freezing as 273.15, and the point water is in the process of boiling as 373.15. The Rankine scale is just like the Kelvin scale. It's an absolute temperature scale. The only difference is you do this entire experiment just described using degrees Fahrenheit instead of Celsius, then shift the scale back and rename it Rankine. The gas graphs will converge at an absolute 0 point of negative 459.67 degrees Fahrenheit. Electric current. I am a mechanical engineer. I do not know much about electricity, but okay, from chemistry, remember everything in the entire universe is made up of protons, neutrons, and electrons. In most solid materials, the atoms and their electrons are pretty much fixed in place, but metals are special in that the electrons kind of free flow around. The nuclei of protons and neutrons stay fixed in place, which preserves the structure of the metal. But it's this sea of electron property that gives metal its, all of its characteristics. It's malleable, ductile, and it conducts electricity. If you start pushing electrons into one side of a metal, then the electrons of that metal will flow out of another path. All electrons have a charge being some sort of property they possess that causes them to repel one another with a certain force and attract protons with a certain force as well. Protons have that exact same charge, so you can use the magnitude of that force to come up with a property called, and you call it charge. That's what charge means. It's just that the fact that push and pull property. The charge of a subatomic particle is quantified using the unit coulomb. You might be wondering why coulombs aren't used as the fundamental unit of electricity. From what I read, the science community goes back and forth between defining the coulomb and the ampere as the fundamental electricity unit. The ampere relates to electric current. An ampere is a certain amount of coulomb charge flowing through a cross-section in 1 second. Well, okay, how much charge flow through a cross-section per second is defined as 1 ampere officially. Again, from what I read, they create current in 2 copper wires a certain distance apart, probably in a vacuum. And when the force on the 2 wires due to magnetism reaches a certain magnitude, whatever the current is at that point, that is the official ampere. But notice the ampere is defined using force. Force is a derived unit. We'll talk about derived units in the next video. Force is derived from the fundamental units of mass, length, and time. So, as of today, you can trace the master reference for the ampere back to the cesium-133 atom and the master kilogram housed in France, or whatever it's housed.